Uh, am I audible? Please let me know if you can hear me. Hello. So welcome to today's discussion session. In the previous class, we actually discussed all the basic part of the soil mechanics. We learned about the soil formation, and then we learned about the uh, basic index properties of soil, and then at last we actually solved some problems that dealt with the index properties of soil. In today's session, what we are going to do is that we will be dealing with the classification of soil. Okay, so soil classification is actually a very important topic, important and basic topic. So whenever we want to construct something on something somewhere, or we want to build something, so we want to construct an embankment, we want to carry soil from one place to other place, and then with that soil we want to construct an embankment, say. So whatever may be the reason, the first basic step is to classify the soil. Okay, so soil classification in that sense is actually very important, and soil classification actually helps us, right? It actually helps us to guess, okay, to guess the uh, engineering properties or the mechanical properties or the mechanical, say the strength it might have. Okay, so just by knowing the type of soil, okay, we can say that okay, this soil might be say weak, or it might be strong. Just we can guess a bit. So in that sense, soil classification is very important. All right. So let us start. So what are the objectives of soil classification? Right. So what is soil classification and what are the objectives of soil classification? Classification means what? To group similar type of items in under one head, right? That is known as classification. So to group soils which show similar behavior, that is known as soil classification. All right. So why soil classification is important? Soil classification is important because it provides us with information about the probable engineering behavior of soil. Okay, not the exact, but we can guess. You can I just have a rough idea what will be the engineering behavior of the soil. Okay, how that soil is going to behave. So we will discuss this in today's class in the later stages, how we can actually guess. So there are different soil classification systems, okay, available to engineers or to uh, uh, people around the world. So there are many soil classification systems. So what we are going to follow is the Indian standard soil classification system. Okay, we are going to focus on the Indian standard soil classification system. Apart from that, we have the USCS soil classification system, that is the Unified Soil Classification System, and we also have the A.S.R soil classification system. Okay, but we are going to focus only on the Indian soil classification system. All right. Now, the Indian soil classification system is actually detailed. Okay, it's actually properly detailed in IS 1498 1970. Okay, okay, this is the IS code that is developed by the Bureau of Indian Standards that actually gives us the soil classification system. Okay, ISS is Indian Standard Soil Classification System, right? Now, what are the major, okay, what are the major big groups where we can classify the soil? Okay, so those are actually tabulated here. So we can see, right? We can see gravel, right? We have gravel, we have sand, we have silt, we have clay, we have organic soil, we have peat. Okay, so these are the prefixes. So Indian soil classification system classifies the soil with a name, okay, with a particular code. That code has two parts, two letters. One is the prefix and one is the suffix. Okay, one is the prefix and one is the suffix. Two letters are there. These two letters actually are used to classify the soil. One is the prefix and other is the suffix. All right. Now, okay. Now, what are the prefixes? Prefixes can be gravel, sand, silt, clay, organic, and silt, peat. Okay. So these are the six prefixes that we may have for any kind of soil. All right. So gravel, sand, these two are coarse grained soil. As we discussed in the previous class, gravel and sand are the coarse grained soils. All right. Coarse grained soils, right? Gravel and sand are coarse grained soil. Silt, clay, these are fine grained soil. Okay, fine grained soil. And then you have organic soil and peat. All right. These are the organic soil means the soils which have more organic content. Okay. That is, they are mostly formed from, say, plant deposits, animal deposits, decomposed, and then those kind of soil are formed. Right? Now let's come to the suffix. The suffix can be well graded W, poorly graded, silty, clayey, L, I, and H. These can be the possible suffixes that we can have here. Right? This can be the possible suffix that we can have. Now, well graded and poorly graded, we'll see how to use this and where to use this. Where to use well graded, where to use poorly graded, where to use this, how we can use these suffixes, we can see. So WPMC, these can be fully understood by well graded, poorly graded, silty, and clay. But what about the other three? LIH. L means when the liquid limit of that particular soil is lesser than 35%, we say low plastic soil, L. And if it's between 35 to 50, liquid limit we say intermediate, and if it's greater than 50, L is greater than 50, we get H, that is high. Okay. Now for gravel and sand. So what can you tell me what are gravel and what are sand? What is gravel and what is sand? So if the particle size is greater than 4.75 mm, if the particle size is greater than 4.75 mm, then we call it gravel. Oh, sorry, sand. Okay. If the particle size is greater than 4.75, sorry, yeah, I'm sorry. If the particle size is greater than 4.75 mm, it is gravel. I was right. Okay. From 80 mm, okay, so from 80 mm to 4.75 mm, that size, that is gravel. If the particle size is lesser than 4.75, lesser than 4.75, but greater than 75 microns, that is 0.075 mm, then that is sand. Okay. If the particle size is lesser than 4.75 but greater than 0.075 mm, then that is sand. If the particle size is greater than 4.75 mm, we call it as gravel. Okay, so what are the possible symbols that we may have for gravel and sand? Those are detailed here. So we can have well graded gravel, poorly graded gravel, silty gravel, clayey gravel, then well graded sand, poorly graded sand, silty sand, or clay sand. When and how we come to these symbols, how we can we'll see this. Okay, so for now, let us just understand that these are the probable symbols that we can have for gravel and sand. Okay. Now for clay and silt. So what is clay and silt? When the particle size is mostly lesser than 75 microns, that is lesser than 0.075 mm, then we call it as clay or silt. Now, if that actually we call it as fine grained soil. We can, so more generic term will be fine grained soil. If the soil particles the size is lesser than 0.075, the more generic term we can use for that is fine grained soil. Now for fine grained soil, okay, now for fine grained soil, if that fine grained soil is non-plastic, that is, it's not plastic, it doesn't have that much plasticity. The plasticity we defined in the previous class from Atterbury limit. So moldable, it's not that moldable, right? Plastic, it is low plastic. The plasticity index is very low. Then that will be automatically sealed. Okay, that will be sealed. And if it is more plastic, obviously it is clay. So what are the, let us see what are the probable symbols that we can have. It can have Ml, Cl, OH, MH, CH, OH, and PT. So for clay and silt, these are the probable symbols that we can have. All right. Now see, so this screenshot I have taken from IS 1490/1970. So here you can see everything that it has been detailed properly. Okay. So first it is so basic. So major classification. If you see here, the major classification are coarse grained component and fine grained component. As I said, coarse grained soil or fine grained soil. So what are coarse grained soil? Size, what? Size greater than 75 micron. Okay. And what are fine grained soil? Size lesser than 75 micron. Correct. So coarse grained soil and fine grained soil. Okay. Now for coarse grained soil, you can see the various classification. Okay. So there various classification are given. So for boulder, it is if the diameter of the particle is greater than 30 mm, that is boulder. Then between 300 and 8, between 380 mm, we are calling it as uh, cobble. Then then we have gravel. If it's greater than 80 mm and lesser than 4.75 mm, we are calling it as gravel. Then we have sand. Okay, so boulder is diameter greater than 300 mm. Cobble is between 380 mm. Gravel is between 4.75 mm. Okay, so gravel, then again it is divided into two parts. You can see here. Here. Then we have sand. So sand is greater than 4.75, less than 75 micron. That is sand. Sand is again classified here. Again, let us come now to fine grain component. So fine grain component we can have clay, silt, or organic matter. Okay, so if so both clay, silt, all these are lesser than 75 micron, but silt, non-plastic behavior or slightly plastic, clay will be more plastic. Okay, exhibit plastic properties. And organic, but organic is organic. Okay, it can be organic means it is organic. Okay, so now let us see. So what we are going to do today is that we will revise a bit. Okay, the first around 45 minutes uh, up till say 7 o'clock, around approximately till 7 o'clock. Let us just revise all the components, revise everything, and then we will actually solve some examples. So when we solve the examples, what will happen? These things will be crystal clear to you. Okay, and anytime you can interrupt me and ask me any question, so I will help you in whatever way I can. Okay, so just let us first revise everything a bit and then we will solve the problems. Okay, of the examples. So yeah, so now see, now let us first deal with coarse soil. Okay, let us first deal with coarse soil. Okay, only coarse soil. Then we will see fine soil. Okay, now let us see coarse grained soil. Now, coarse grained soil means, say we have a certain amount of soil in your hand. Okay, say 5.5 kg of soil. Now what we do, you do sieve analysis. Okay, you do sieve analysis. Sieve analysis we discussed in the previous class. Okay, we do sieve analysis. Now after doing sieve analysis, we find that more than 50% of the soil fraction that you have analyzed sieved, that is greater than 4.75 mm size, and so that is, sorry, that is uh, that more than 50% of the fraction is actually less than 75 greater than 475 micron. Means after sieve analysis we have found that more than 50% of soil is greater than 75 microns. Okay, more than 50%, say 500 grams you have sieved. So in 500 grams, 400 grams, okay, 400 grams or say 450 grams is actually having size which is greater than 75 micron. So this means the total fraction can be identified as a coarse soil. Okay, coarse soil. Now when the fine fraction in that coarse soil, that means the soil is coarse soil. Now, if the fine fraction, the amount of fine particles in their coarse soil is actually less than 5%, then we classify the soil exclusively on the basis of grain and gradation. Okay, okay, understood? Grain and gradation means it will be either first term will be, see, first we identified that the soil is coarse grained soil. That means either sand or gravel, S or G. Done. Now comes to the second, the suffix part. Now suffix, if the fine fraction in that soil is less than 5%, then we can say that, okay, whenever I say fine fraction, that should come to your mind that fine fraction means soil passing 75 micron sieve. Fine fraction means that soil passing 75 micron sieve, that means soil size lesser than 75 micron. That is the fine fraction. So that fraction, if the fine fraction is less than 5%, okay, if the fine fraction is actually less than 5%, then we classify on the basis of grain gradation. The prefix is decided, prefix will be either G or S, and what about the suffix? Suffix will be, we can have two suffixes, either poorly graded or well graded. Either well graded, poorly graded, either well graded, poorly graded. Okay, so in detail we will see how well graded, poorly graded, all these things we are classifying. Now, second thing can be, if the soil is fine, say 50% of the total soil, the 450 grams out of 500 grams is passing through 75 micron. That means our total soil is fine. If the soil is fine, then what do we use? We use this chart. Okay, this chart to actually plasticity chart to actually identify to classify the soil. We will see. Okay, we will see how you can use that. So if the soil particle falls below this line, that is sealed. If it falls above the line, okay, if it falls above the line, it will be clay. If it falls below the line, it will be sealed. Okay, just have a look at this chart properly. Okay, and just see this line, A line. This line is called the A line, and there is an equation of A line where plasticity index is equal to 0.73 liquid limit minus 20. This is the equation of A line. Okay. Okay, this is clear, right? So now let us see next. Now, when the fine fraction, so first we decide so that if the fine fraction in a coarse soil, okay, our soil is coarse, it is more than 50% of the soil is coarse soil. Okay, coarse soil means greater than 75 micron size. More than 50% of the soil has size greater than 75 micron. Now, when the fine fraction in a coarse soil, so first we saw the when the fine fraction in a coarse soil is less than 5%. That time we are classifying using this. Okay, either it will be GWGP or SWSP. These are the probable. Now, if the fine fraction in a coarse soil, okay, if the fine fraction in a coarse soil is greater than 12%, greater than 12%, then instead of well graded and poorly graded, W and P, it is a gradation, we use the fine particle nomenclature. That is, it can be either clay gravel or silty gravel, clay sand or silty sand. So first, the prefix will be same gravel or sand, but the suffix now in the previous case, the suffix was what? Suffix was occupied by the gradation. This is well graded or poorly graded. Now, in this case, the suffix will be actually suffix will be occupied by the fine particle name, either C or M, that is clay or C. Okay, based on where it falls on the A line, above or below. Now, the third case can be when the fine fraction in a coarse soil is between 5 and 12%. Okay, when the fine fraction in a coarse soil is between 5 and 12%. In that case, what will we do? In that case, we have to use dual classification. That is, both the gradation and the this fine name will come. So, what are the probable? GWGC, GWGM, same GPDC, GPGM. Similarly, S also we can have. Okay, SWSC, SWSM, SP, SC, SP, SM. Okay, okay. Now, can can fine grade soil. Okay, so these are what? These are basically all are coarse grained soil, right? These everything is coarse grained soil. Okay, now let us come to fine grained soil. Now, can fine grained soil have dual symbol? Okay, similar to coarse grained soil, can fine grained soil. So when I say fine grained soil, that means more than 50% of the soil fraction is lesser than 75 microns. So can fine grained soil have dual symbol? So answer is yes. Yes, fine grained soils can have dual symbols. And what are the possible dual symbols for fine grained soil? These are given here: CLML, CIMI, CHMH, MLMI, MIMH, CLCI, CICH, OLY, YOH. So when do we have CLML? So if you see the this plasticity chart, you can have if the soil falls in this region, in this shaded region, we will have CLML. Okay. Now when will we have CIMI? Say this is the chart, right? Plasticity chart. Now in the plasticity chart, say this is liquid limit and this is the plasticity index. Okay. This is the 35% liquid limit line. This is the 50% liquid limit. Now say our soil plots very close to this A line here in this region. Okay, in this region. Then we can have CIMI. Now if the soil plots here, then we can very close, but in this region we can have CHMH. Okay, CHMH. Now MIMH, when will you have this? Here. Okay, so MIMH will be here. Okay, that means MLMI, right? So here, very close to here. Then we will have MLMI. Okay, MIMH when here. In that case, we will have MIMH. Okay, so again, I will say one by one. CLML where in this region that I showed earlier, CLML, CIMI in this region, in this dotted portion. This will be CIMI, CIMI here. Okay, here in this region we will have CIMI only very near to the A line. That time we will have dual classification. Now CHMH means here. Yeah, understood. Here, this one CHMH. Now MLMI when here. MIMH when here. Okay. CLC that is very boundary. It is near to these boundaries but not crossing. So that time we have to use dual classification. CLCI when where is CLCI? CLCI means sorry M I was saying na. Just a second. Just a second. Let me just show you clearly. Otherwise it will be you will get confused. Okay. 35%, 50%. Okay. This is IP. All right. So if it falls below a line, we know it is silt. If it falls above a line, we know clay. Right? So here it's clay, here everything is silt. Below a line, it's silt, above a line, it's clay. Clear? Now when CLML is a special case when it falls in this region. It is shown in the A line. CIMI. CIMI when do you have CIMI? CIMI is here. Here. Then CIMI. Okay, here or down also we can have. Okay, CIMI. Where CHMH is here or below that. Okay, or below that also. Very near. MLMI here. Here or here. Here, very close. Okay, this is MLMI. MIMH here in this region. CLCI. CLCI where? Here or here. CICH where? Here or here. Very close to LM. OLY also this one same as MLMI OI. This is same as M, okay, but organic, right? So I hope you understand these things, okay? Whenever it is very close to these boundaries, so these are the boundaries, right? These are the boundaries. These lines are the boundaries. Whenever the soil plots very close to the these boundaries, what we have to do? We have to use dual classification, right? So everything will be clear once we solve. Now, what are the steps for soil classification? So the first is grain size distribution. To plot the grain size distribution, how we can get this from sieve analysis? Okay, we discussed sieve analysis in detail in the previous session, right? Now, from the sieve analysis, if you see, if more than 50% retained on 75 micron, then it is coarse. Okay, if more than 50% is retained on 75 micron sheet, then it is coarse soil. Now, if more than 50%, first check that if more than 50% is retained on 75 micron, then first you have identified that it is coarse soil. Now, which coarse, gravel or sand? That you have to identify. First, we have identified that more than 50% is retained on 75 micron C. Correct? Now, so from this, you can say that the soil is coarse soil. Now, what type of coarse? Either it is uh, sand or it is gravel. Okay, whether it is sand or whether it is uh, gravel. How can we know? If more than 55% retained on 4.75 mm, then that is gravel. And if more than 50% retained, sorry, not retained, really better if I write, if more than 50% passes 4.75, then it is sand. Okay, so understood, right? Now, now you have identified. So your prefix is finalized now. First, you identified that it is coarse soil. Then you identify whether it is going to be G or S. Now you have to identify the suffix, right? You have to identify the suffix part. Now, in order to identify the suffix, what we have to do is that we have to what? We have to see the fine fraction. Now, if fine fraction, so whenever I say fine fraction, what did I tell? Whenever I say that term fine fraction, that thing should come to your mind. That fine fraction means fraction that is passing through 75 micron sieve, right? That is the fine fraction. Fraction that is passing through 75 micron sieve, that is the fine fraction. Now, if fine fraction is less than 5%, then the suffix will be either well graded or poorly graded. Okay, as we discussed in the previous slides, it will be either well graded. Now, if it is fine fraction is greater than 12%, then it will be either clay or silt. If the fine fraction is between 5% or 12%, our suffix will be dual. Our classification will be dual classification. Okay, so just remember this. We will, when we solve the example, this will be clear. So if the fine fraction is less than 5%, it will be either well W or P. The suffix will be W or P. Greater than 12, it will be C or M. And 5 to 12, it will be 12 classification. Now let us come to the. Okay, this is 3. Now say if from sieve analysis you find that more than 50% is passing 75 micron. What does this mean? More than 50% is passing 75 micron. That means, as I said, this is the fine grained soil. Fine soil. Now you have to identify whether it is a silt or clay. Right? Now you have to identify whether it is a silt or clay. Now, how will we identify? We have to use this chart, plasticity chart. If the soil plots here, it will be silt. If it plots above, it will be clay. Okay, so now your suffix is identified. Either it will be C or M, silt, clay or silt. Now, what about the suffix? A suffix can be what? Suffix can be L, I, or H. Based on what? Based on the liquid limit. If liquid limit is less than 35% liquid limit is less than L. If it's between 35 to 50 I, and if it's greater than 50, it's going to be H. Okay. Now there can be one more tricky situation, right? There can be one more tricky situation. Say, say 50%. So this is actually impossible, just a theoretical, like theoretical situation. Okay, in practical scenario, it's hardly, like there is very less probability that you are going to encounter this situation. Okay, so this is just a hypothetical situation. Hypothetical situation is that 50% is greater than 75, 50% is passing through 75 micron, 50% is retained on 70. So 50-50. 50% fine, 50% coarse. Then how are you going to classify? If this is the case, then how are you going to classify if the case is of 50-50? Okay. So in that case, what you have to do, you have to use again dual classification. Say, for say it is sand, so sand SP or SM, or then we have to again classify it as clay and type of clay, say L or I or H. Okay, like this, we have to use some dual classification. Okay, example, say 50-50, 50 for 50-50 case. 50% is coarse fraction, 50% is fine fraction. In that case, 50-50. Okay, so when we solve the examples, this all this will be like very clear to you. Okay, as we solve the examples, these things will be clear, more clear. Okay, so now one more topic that was discussed, that is the soil structure. Okay, this part that is not so important. This portion is not that important, but still we should you should know. So this soil structure, this part is not that important, but more important the part is this clay minerals. This clay mineral, this part is actually a little bit more important than the soil structure. So what is soil structure? So soil structure is nothing but the mode of arrangement of soil particles plus the forces between them. Okay, that hold together. These together they are known as soil. This is called as soil structure. Okay, so in coarse grained soil, the thing that the main predominant force that exists between the particle, that is the gravitational force. Okay, but in the fine grained soil, the main predominant forces are the surface bonding forces. Okay, because they are very small in sizes and they have more surface area. Okay, due to that, there are some surface bonding forces that are dominant in the fine grained soils. Okay, now there is one thing which is defined as specific surface. What is specific surface? The ratio of surface area of the material to its mass or volume, that is known as specific surface. So for fine grained soil, the specific surface is very huge. Okay, the specific surface is actually very large for fine grained soil. Okay, specific surface is actually very large. The specific surface actually determines which is dominant, gravity or the surface bonding. So if the specific surface area is very large, that means the soil is fine grained. That means the surface bonding forces are going to be dominant. And if the specific surface is lesser, that means the gravity is going to be more dominant. Okay. Now, clay soil are made up of clay minerals, which has plasticity and cohesion. Clay minerals are electrochemically active. As I said, clay are fine-grained soils, and that's why they are electrochemically active. So, chemical weathering forms clay minerals that we already had discussed in the previous class. So, chemical weathering forms clay minerals. Now, clay minerals are basically divided uh, onto three groups. So, what are clay minerals? Clay minerals are the basic constituents. Just a second. See, fine means what? Fine means the area to volume ratio, right? That's why. Say you have uh, what to say? How to explain to you? Say you have this brick. Okay, you have this brick. Now this, so now if we divide, this is some volume, right? This is some volume. Okay, in now if you, now we can, what we can do, we can calculate the surface area, area of this, 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 area of this. It will give the surface area. So that area divided by this volume, it will give the specific surface. Now see, if we divide it into very fine rectangles, very fine rectangles, obviously the surface areas are going to increase, right? So we say, say you divide this into two parts. Okay, now say this side one area is going to increase. How to explain? One area is going to increase, right? Say, uh, if I have a box, I can actually explain it to you. Hmm, how to explain? Very difficult to explain actually. Just try to understand. Okay, say you have this. Say you have this. Okay, okay. Now this brick is there. Okay, this, you have a brick. This brick is there. Okay, you have this brick. Now, say if we cut this brick here, okay, it will you will have now two pieces. You have two pieces. Now see, now this area and this face, that face also is going to have one more area. One, this one, this area is increasing, right? So if you divide it into this very small portion, these areas are going to get increased. Surface area is going to get increased. So similarly, see here, this one additional, this before, say before, this was just a whole block, right? Now you are dividing it. So this area, this one additional area is actually coming here. So that's why whenever, how many, in how many parts you go and dividing that, this surface area is going to get increased. But in the same volume, the surface area is going to get increased. Okay, that's how fine particles, similar to these fine particles, have more specific surface. In the same volume, in that same volume, the surface area is actually larger. Okay. Okay, I hope you, it is clear from this brick example. I hope it is clear. So before, you are having this area, this whole area, this area, bottom area, and is our, what is the question? If we consider only one particle of fine, I did not understand. What if we consider only one particle of fine? No, see, the thing is that coarse means what? Coarse means that is the minimum size of particle that you can have, right? So you cannot go smaller than that in coarse soils. That is the size, inherent size it is going to have. In fine soil, what? Fine soil, the sizes are very small. Okay, that is the inherent size. You are not, you yourselves are not grinding it and making it small. Inherent nature, by nature, the particle size is very less. Okay, coarse soil. If you now break the coarse soil, yeah, I understand. Now, if you break the coarse soil, you make some machine where you can break the coarse grain into very fine. You can, that time, see, that time you can make the surface area. You can have high surface area, but that time that particle is not going to be coarse anymore, right? It is going to be fine. It is going to change into fine. So that is the thing. Okay. So clay minerals are divided into three groups based on their crystalline arrangement: kaolin, montmorillonite, and elite. So these are the constituent minerals that form a clay. Okay. Now these clay minerals are actually formed by arrangement of some crystal sheets. So there are two kinds of sheet: tetrahedral sheet and octahedral sheet. So now, with various arrangement of this tetrahedral and octahedral sheet, and the bonding forces between them, we can have these minerals. So these sheets actually combine to form minerals. Various arrangement of the sheets and the how these sheets are actually bonded to each other, they determine what kind of mineral you are going to have. Whether you are going to have kaolin, whether you are going to have montmorillonite, whether you are going to have elite. Understood? So the arrangement of this actually forms the uh, minerals. Arrangement of these crystal sheets actually form the minerals. So the stacking, nature of bonding, and metallic ion in the lattice differentiate them. Okay. So this thing, I think, I hope it is clear. If you see if you have gone through the lectures in the class, I think that was clear. Still, see, silica sheet I will draw for you. So silica sheet is nothing but you have four oxygen atoms. Okay, you have four oxygen atoms, and in the middle you have one silicon atom. So four oxygen and one silicon. This forms the silica sheet. Similarly, in octahedral alumina sheets, what you have? You have six OH minus ions. Okay, OH minus ions that uh, that are actually this that actually enclose. So six ions. Similar to this, we will have six at the outside, six OH minus outside, and inside. Say inside, if we have aluminum, here it is silica, right? Inside, if we have aluminum, then it is gypsite. It is a gypsite sheet, and inside, if you have magnesium, that is nothing but brucite. Brucite. Okay, that is the difference. So one more topic is this isomorphous substitution. Okay, this you might hear this term isomorphous substitution. So what is isomorphous substitution? In clay mineral lattice, metallic ions may be substituted by other metallic ions having lower valence but similar size. So this is known as isomorphous substitution. Okay, say you have a uh, mineral lattice. So you have some stacking of some mineral. Right. Here, say you have some aluminum ion. So now if this aluminum is replaced by some other ion of similar size, that is nothing. That phenomenon is known as isomorphous substitution. Okay. Now the arrangement of uh, these sheets, that is the gypsite and this just a second. Just a second. Huh? Just a second. Give me a second. Huh? Yeah. So I was saying that now the arrangement, okay, the arrangement and the bonding and the type of ions that is there in between the silica sheet or the alumina sheet, that will actually determine the mineral type. So in kaolinite, what is there is that we have one gypsite sheet, okay, then we have one silica sheet, okay, then again this is repeated, one gypsite sheet, one then silica sheet, this is repeated, and in between this we have hydrogen bond, H bond. So if you recall from your chemistry classes in class 2, you can remember that for hydrogen bond is actually very strong. As hydrogen bond is very strong, this bond is very stable, and that's why the clay which is made up of kaolin mineral, those are least active. Okay, these are least active. Clay that is made up of kaolin, it is least active. Now another mineral is montmorillonite. What is montmorillonite? Similar, so there's different arrangement. Here we have silica, then we have gypsite, then again we have silica like this. Okay, that's silica, gypsite, silica. Like this, it continues. Okay, silica, gypsite, silica, silica, gypsite. Like this, it continues. Now here, the bonding is very weak. Okay, the bonding is weak. Weak van der Waals bond. Okay, the bonding between the sheet is very weak. So what happens? The clay mineral that are the clays that are formed from montmorillonite minerals. What happens in that case? In that case, actually, what happens is that they can absorb water. Water, that is, it can absorb water on its surface and swell to a large amount. It can hold a huge amount of water on its surface. Okay, so we'll see that for montmorillonite actually the liquid limit is very high. Okay, example of a soil which contains this montmorillonite is the black cotton soil. Okay, so this soil actually has montmorillonite. So due to the presence of montmorillonite, due to because this type of soil is made up of montmorillonite, what happens? This can swell to a large amount by absorbing water because the in between the sheets the bonding is very weak. So H2O particles can easily enter here. Okay, enter here and enter into this between the lattice. Okay, and there is one more mineral, that is the elite mineral. In elite mineral is also similar to montmorillonite, but what happens? Okay, what happens? So this is also similar to montmorillonite, but here in between we have some potassium ions. Okay, the bonding is formed by potassium ions. So due to the presence of potassium ions, what happens? This bond is little bit stronger than the van der Waals, van der ionic bond, right? Ionic bond. So this is little bit stronger than this. This is little bit stronger than this bond is little bit stronger than the van der Waals. So this type of the clay which is formed from elite actually soil lesser. Okay. So montmorillonite will have the highest liquid limit, then we will have I, then we will have uh, this like a kaolinite. So this will be the arrangement. Okay. Now what is clay particle interaction? So what will happen? So in aqueous environment, it is in presence of water, the clay particles may either flocculate or either they may disperse. So flocculation means this is the particle, right? So you may join together like this. Two particles may join get joined together like this and flocculate. This is known as flocculation. And what is dispersion? Dispersion means they will go away from each other like this, like this. They will move away from each other. It is dispersion. So in aqueous environment, clay particles may either flocculate or they may show dispersion. So flocculation generally occurs in H2 phase configuration, and dispersion only phase to phase configuration. Okay, right? So this was all. Now let us start solving some examples. The main part. Let's come to the main part. Start solving the examples one by one. So that this classification portion is actually crystal clear to us. Okay. So that this classification portion is very clear to us. Okay. Now the first problem. Okay. Slowly we are going to solve. Okay, one by one. So if there is any problem, just ping me anytime. Slowly, we will be solving it together one by okay, so from the grain size distribution data given below, classify the soil. So we have a grain size distribution data that is given to us. The size of particle is given and the percentage finer is given. Okay, size of particle is given and percentage finer. So percentage finer than 0.48 is 60%, percentage finer than 0.33 is 30%, percentage finer than 0.21 is 10%. Now, see, in the question, it is clearly given that classify the coarse soil. So this makes your task easier, right? The soil is coarse soil. So now, if the soil is coarse soil, it can be either what? Sand or gravel, right? The soil can be either what? Sand or gravel. If the soil is coarse, it can be either sand or it can be either gravel, right? Now, you are saying this is coarse sand. How it is coarse sand? Sand. So if the particle size is lesser than 4.75 mm, that coarse soil will be sand. It will be sand, not gravel. That is so this so if you see the particle size less, so more than 100% of the soil is actually lesser than smaller than 4.75 mm. That's why this soil is sand. So let us make. Okay, so first the prefix we have identified sand. Now what about the suffix? What about the suffix? Now the first thing that we have to check is that whether there is fine fraction in this soil or not. So, and if so, what is the percentage finer? Okay, so what is the percentage finer? So see now, actually it is given that uh, percentage finer than 0.21 mm is actually 10%. Now nothing is actually in this question is little bit oblivious because not because see because nothing is actually mentioned about the size that is lesser than 75 micron. Okay, nothing is mentioned about the size 75 micron. Okay, if more than if say now see 10% lesser than finer than 0.21 mm is 10%. So this is our boundary for fine grain, right? So now nothing is mentioned actually in this question that whether some 5 per so whether some amount is actually passing through 75 micron or not. So in this question, let us assume that the fine fraction passing through 75 micron is less than 5%. Okay, the fine fraction, that is the fraction passing through 75 micron sieve, that is actually less than 5%. Let us assume. So in that case, what will happen? So there can be two options here for the suffixes. It can be either well graded sand or poorly graded sand, right? Well graded sand or poorly graded sand. Now, how to identify well graded or poorly graded? For that, we will use the two terms that we had defined in the previous class while we studied the sieve analysis portion, right? You will define these two terms. One is the coefficient of uniformity and the coefficient of curvature. So what is coefficient of uniformity? D60 by D10. What is the D60 size? We can directly have D60 size is 0.48. D10 size is 0.21. So what is CU? CU is 2.28. And another term is coefficient of curvature. That is D30 square by D60 into D10. So what is D30 square? 0.33 square. We're going to have 1.7. Now, if we recall from the previous class, for well-graded coarse soil, That so for well-graded sand, the Cu should be actually greater than 6. But here it is not greater than 6. And the Cc should be between 1 and 3. This condition is satisfied. Cc should be between 1 and 3. This condition is satisfied. But Cu is not greater than 6. So we can say that this is a poorly graded sample. So we left SP. So the final soil classification will be SP. That is poorly graded sand. Okay, so this is how we have to classify. Now let us see the next similar question. Sieve of size is sieve size is given, percentage fine is given. So percentage finer than 4.75 mm is 80% and percentage finer than 75 microns is 7 mm. So the fine fraction is between 5 and 12%. Note this, fine fraction between 5 and 12%. Okay, because it is 7%. 80% is passing through 4.75 mm, and obviously less than 50% is passing through 75 microns. So that obviously this is going to be sand again. So prefix is identified as sand again. Right, now you tell me what will be the second part. What will be the second part? Now first, you see, fine fraction is between 5 and 12%, right? Fine fraction is 5 and 12%. That means what? That means we need to have dual classification. That means it is either going to be, so it is going to be like this. So this term will be either clay or silt, and this term will be either well graded or poor graded. Okay, dual classifications, right? Okay, dual classification. Why dual classification? Why dual classification? Because the fine fraction is between 5 and 12%. So you are saying what? You are saying uh, S SLSM. No, not like that. Not SLSM. See, the first part, this will be either W or P. Second part, this will be C or M. So let us see the first part first. So here it is said that given the size of aggregates very linearly. So there is linear variation of the size. So what we can do is you can use this data to find out the D60, D30 and D10. So that we can calculate Cu and Cc, so that we can find whether it is well graded or poorly graded. So let us do interpolation and find it out. D60. So if we solve this, if we do this interpolation, you will get D60 at 3.47. Similarly, what we have to do, you need to find D30. From here, you will get D30 as 1.548 mm. Okay. Now for D10, we need to find D10 also, right? So same. We will get D10 sizes 0.267. So here it is given that the size varies linearly. Okay, it is given that the size varies linearly. That is the reason what we did was we did some linear interpolation to find out the D10, D60 and D30 sizes. Okay, now as we know the D60, D10 and D30, please calculate the Cu and Cc, same as the same way you calculated in the previous problem. Please calculate Cu and Cc. So what is Cu? Cu is d60 by d10 and Cc is d30 square by d10 into d60. Please calculate Cu and Cc. Yeah. So Cu will be 12.9. Okay, 12.97. And what is Cc? What is Cc? How much will be Cc? d30 square by d10 into d60. 2.68. Okay, 2.6. So, Cu is greater than 6. Cu is greater than 6 and Cc lies between Cu is greater than 6 and Cc lies between 1 and 3. So what can we say? This will be well graded or poorly graded? Well graded or poorly graded? Cu is greater than 6 and Cc is between 1 and 3. So what will be this one? Well graded or poorly graded sample? Obviously, it is going to be well graded, right? Well graded. Now for the second part, see in the question, there is no mention of plasticity index and liquid limit. Okay, there is no question. But one thing is mentioned in the question is that the fine fraction is non-plastic. So fine fraction is non-plastic. What does this mean? It will be what? If the fine fraction is non-plastic, what does this mean? This will be silt or clay. If the fine fraction is non-plastic, what is the fine fraction? Silt or clay? The fine fraction is non-plastic. Yeah, correct. It will be silt. That is SM. So our final classification will be SW SM. Will be the final classification. So well graded sand, silty sand. So this is the classification. Okay. Now let us see the next one. From the sieve analysis data, classify the soil. Given total weight of the soil sample using sieve analysis is 500 grams. So in order to do this, what we will do, so sieve sizes are given and weight retained on the sieve are given. So what we will do is that we will just make a small table. Sieve size, weight retained, percentage weight retained, then cumulative percentage weight retained and percentage final. So first sieve size is 0.6 mm. What is the weight retained? 200 grams. Percentage weight retained 200 divided by total weight 500. 200 by 500 into 100%, that is 40%. Then we have 0.5 to 50 grams. That means 50% weight retained. And then we have 0.4 to 5, that is 50 grams. 50 grams in percentage, what will be this? This will be 50 by 500, that is 10%. Now let us calculate the cumulative weight retained. Cumulative weight retained means, so we have first 40%, then 40 plus 50, 90%, then we have 100%. Now percentage final 100. If you deduct 100 from cumulative weight retained, we will get the percentage final, right? So 100 minus 40, 60%, 10%, 0%. Now tell me what kind of soil this is. Is it a coarse soil or fine soil? First tell me this, whether it is a coarse soil or it is a fine soil. Coarse soil or fine soil? This is a coarse soil, correct. This is a coarse soil. This soil is obviously a coarse soil. Why it is a coarse soil? Because most of the all the fraction is actually size of the soil is actually greater than 75 mm. That's why you're calling it as a coarse soil. Now, whether the soil is now you first you have identified that this is a coarse soil. Identified coarse. The second step is to identify what type of coarse soil, sand or gravel. What type of coarse soil, sand or gravel? You've identified the soil is coarse soil. Now just tell me what is the type of sand here. It is a sand. Why it is a sand? Because size is smaller than 4.75 mm. That's why it's sand. So second part you identified, this is sand. Now the finer there is 0% fine in the soil. So obviously the total classification is going to be on based on the gradation. Now let us try to find out. Can we find out the gradation? Well graded or poorly graded? Can we find it out from this data? So what we can do, you can see 60 and D60 and D10 are actually given here. Okay, from here you can get D60 and D10. So what we can do, you can get coefficient of uniformity D60 by D10. So what is D60? D60 is 0.6, D10 is 0.5. So if we do this, it will be 1.2. So CU is 1.2, right? CU is 1.2. This is not greater than 6. So what? That means the soil is poorly graded. So what will be our what will the final classification? It will be what? Tell me. It will be as sand and poorly graded. So poorly graded soil, SP. So this is going to be the final classification. Okay. Let us come to the next problem. From the sieve analysis data, classify the soil. Given total weight of sample used in sieve analysis in is 1000 gram, it is 1 kg. Liquid limit is given, plastic limit is given. Now, first again, what we will do, let us just similar to the previous problem, let us write everything. 4.75, 0.07. What is the weight retained? 20 gram. Now, percentage weight retained 20 divided by 1000, that is 2%. 730 divided by 7, 73%. Cumulative retained. Percentage finer. How much? 98% and 100 minus 75, 25%. This is the similar to the previous one. Okay. Now, tell me whether it is a coarse soil or fine soil. Coarse soil or fine soil. First, you need to identify this. The first step is to identify whether the soil is majorly coarse or fine. Whether the soil is coarse or fine. So percentage finer than 4.75 mm is 98% and percentage finer than 75 micron is 25%. So tell me whether the soil is coarse or fine. What will be the answer? That the soil is coarse or fine. How no? How fine? How are you saying this is fine? Whenever more than 50% is actually finer than 75 mmc, 75 microns, at that time you can say that the soil is fine. Okay, but here only 25% is finer than 0.075, right? That's why the soil is coarse only. And in coarse also it will be sand. Okay, because 98% is passing through 4.75. Understood why it is coarse? Because more than, see, if the fine, that is if the percentage that is finer than 75 micron is more than 50%. If that is more than 50% finer, then that is, we can call it a fine soil. But here it is 25%, right? Here, sorry, here corresponding to 75 microns, only 25% is finer. That's why it is a coarse soil, not a fine soil. Okay. Now in coarse soil, what is the coarse soil? Sand, obviously sand, right? Obviously it's going to be sand. S. Now the second target is to determine the, yes, correct, sand. The second target is to determine the suffix. How to determine the suffix? For the suffix, what we need to do is that here for the suffix, first we have to look at the fine fraction. So what is the fine fraction here? Tell me, what percent is the fine fraction? 25%, right? 25% is passing through 75 micron sip. That means 25% is the fine fraction. Now this 25% is greater than 12%. That means what? That means we have to use either, we have to use the this fine classification for the suffix. Okay, so how will we use the, what are the possible suffixes that we can have here? We can have either clay or silt. Correct? Clay or silt. Now we have to identify whether this is clay or silt. How can we do that? As I had discussed it, I had discussed this in this class. How are we going to do this? We are going to take help of this plasticity chart. Okay, we are going to take help of this plasticity chart in order to determine whether it is a clay or silt. Now, let us first determine our plasticity index. So, what is plasticity index? Is liquid limit minus plastic limit. So, what is liquid limit? 40% minus plastic limit is 18%. So, how much is it? 22%, right? 22% is the our liquid limit. The liquid limit of our, so the plasticity index of our sample, that is 22%. 22% is the plasticity index of our sample. Now, now let us find the plasticity index from this chart, from the A line. So what is the A line equation? 0.73 liquid limit minus 20. So 0.73 40 minus 20. It is going to be how much? How much? 14.6%. Okay, 14.6%. Now tell me whether our soil is going to plot above here or here, below the A line, above or below. Whether our soil is going to plot above the A line or, yeah, correct. Why above? Because this 22% is actually greater than 14.6%. So if it plots above the A line, then what is going to be the suffix clay or silt? Above the A line, what is it going to be? C or M? Above the line, correct. It is going to be C. So above the line means it. So it is going to be C. So our soil is SC. It is clayey sand. The soil is clayey sand. Okay. Okay. Done. So again, one more, classify a clay soil if it has a liquid limit of 40% and plasticity index of 28%. So in the question only it is given clay soil. So you don't need to worry about the prefix part. You know it is clay. C. Now you need to identify the second part. Okay, you know it is first portion is C. You need to identify the prefix. You already know it is going to be clay. C. A suffix we going to okay, the recording of the classes I will give you the link is actually, I don't know why it is not shared. I will share the link with you. Okay, I will share the link. Just hold on. After we after we finish discussing the problems, I will share the link. All right. There you can actually get this one, the details. So what I will do is that what I can do is that just I will share the link of the I will share the link of the YouTube channel, okay, where I'm going to upload all these things. After each class I will upload all these things in that YouTube channel. That link I will share to you, and also I will share to you the link of the Google Drive folder where all this presentation that I will upload it. Okay, that PDF file you will get that there. Okay, these two links I will share to you. Just let me finish. Let us just finish discussing all the problems, and before ending the meeting, I will share to you. Okay. So here we have the first. So the first part is this clay C. We have identified uh, this is C. Okay, clay from the question only. Now we have to identify the second part. Okay, the suffix part. So what the suffix is going to be? Now liquid limit plasticity index is given. Okay, the plasticity index is actually given to us 28%. Now let us calculate the plasticity index from the A line. IP is equal to 0.73, same. Liquid limit minus 20, 40 minus 20, 14.6%. Now tell me, okay, 14.6%. Okay, so just you can recheck it once. So 14.6%, right? And our plasticity index is 28%. So obviously it is plotting above the A line. So obviously it is going to be clay. Okay, the question also the data also corroborates whatever it's given in the question. Correct? Done. Now we have to determine the suffix part, right? So for suffix part is very easy. Just you need to look at the liquid limit. So liquid limit is 40%. Right. If it is 40%, that means what? Between 35 and 50%. Between 35 and 50%. That means what? What will be the suffix? Tell me. It is between 35 and 50, right? So it falls in this region. So what it is going to be? If liquid limit is 40%, that means what? That means it is between 35 and 50%. So obviously it is going to be intermediate. I. So the soil is classified as CI, intermediate plastic clay. Why intermediate? Because the liquid limit of the soil falls between 35 and 50%. If the liquid limit is greater than 50%, it would have been H. If it is less than 35%, it would have been low, L. As the liquid limit is between 35 and 50%, we are giving it as I, intermediate, I. Okay, done. Okay, this is the next question. Classify a soil sample if it has a liquid limit and plastic limit. Liquid limit 40%, plastic limit 30%. Liquid limit is 40%, plastic limit is 30%. The percentage passing through 4.75 mm is 65%, and that through 0.05 mm is 58%. Okay, just try to solve this one by yourself once. I will give you 5 minutes. Just try to solve this one by yourself. Okay, try to solve this one. The plasticity, liquid limit is given, plastic limit is given, the percentage passing through 4.75 mm, the 65% is finer than 4.75 mm, and 58% is finer than 75 microns, 0.075 mm. Okay, that this data is given to you. Just try to do it by yourself. Okay, Vinod, no issues. This Shubham, can you try, please? Please try. You are saying is MH. Okay, let us see. You are saying MH. You are close, but it is not correct. Just think whether it will be MH or something else. You are half is 50% you are correct, but 50% you are wrong. ML, no, not ML also. How ML? See, liquid limit is 40%. Liquid limit is 40%. If liquid limit is 40% means what? Between 35 and 50, right? It is going to be, no, it is going to be I, intermediate. ML is less than 35%. H is greater than 50%. Between 35 and 50%, if liquid limit falls, that is I. Okay. Uh, so now let us see. Now first, so now step by step, let us see how we came to this. First step, identify whether the soil is coarse or fine. Whether the soil is coarse or fine. That is the first step. Now, how can we identify this? Now see, by seeing the percentage finer data. So 65% is finer than 4.75 mm and 58% is finer than 0.075 mm. That means more than 50% is finer than 75 microns. More than 50% is finer than 75 microns. That means the soil is definitely a fine soil. More than 50% is finer than 75 microns. That means the soil is definitely a fine soil. More than 50%, more than 50% is more than 50% is finer than 75 micron. That means it is a fine soil. Correct. Now we have identified the soil is fine. Now we have to identify what kind of fine. What kind of fine? Whether it is clay or whether it is silt. Whether it is C or whether it is M. Clay or silt. You have to identify. Now, how to identify whether it is clay or silt? We have to take help of our plasticity chart. So in a given case, what is the liquid plasticity index? Find out the plasticity index. Liquid limit minus plastic limit. So liquid limit is 40 minus 30. Sometimes plasticity index is 10%. Now plasticity index from the A line. N3 liquid limit minus 20. 14 point. How much? 14.6%. That means as 10% is the plasticity index that our soil is having, and IP is the plasticity index from, that the A line is giving, right? At the A line. So obviously 10% is lesser than 14.6%. Right? This means what? This means the soil is going to plot below the A line. Below the A line. So if the soil plots below the A line, definitely it is going to be silt. M. Okay, definitely it is going to be silt. M. Now you have identified the first part. Okay, 50% if your problem is over. Silt. Now we have to come to the suffix part. Now for the suffix part, very easy. You have to identify using what? Using the liquid limit. So the liquid limit is what? 40%. Now 40% lies between 35 to 50%. So if the liquid limit is less than 35%, less than 35% liquid limit, then it is low. If it is greater than 50%, it is high. Between 35 to 50%, it is intermediate. So this is 40% is between 35 to 50%. Obviously, it is going to be intermediate. So this is the soil, intermediate plastic silt. Okay. So this silt, this can also be OI also. Okay. Organic also. Okay, this can be OI also. OI, how can we? So how can we differentiate between a silt soil and an organic soil? So by smell. So organic soil, it has some organic content, right? Due to decay of organic matter, it has some organic content. So you will have some distinct color and smell. Okay, so it will be Mi or Oi. Now solve this problem. Classify a soil sample if it has a liquid limit 40%, plasticity index 10%, liquid limit of oven dried sample is 25%, the percent passing through 75 micron is 62%. Okay, try to solve this one and also take help of whatever is written here. I've given some note here. Okay, note here. Just try to take help of this and solve this. Okay, I will give you 2 minutes. Just try once. Just try similar to the previous problem. Okay, Vinod, I hope you can try now because this is almost similar to the previous problem. Just try. Even if it is wrong, no issues. We'll try again to solve. Just try. Just have a try. Just try to guess. Okay, guesstimate. Guess or logic. Try to classify. Just try. First, tell me whether the soil is coarse or fine. Tell me this. Whether the soil is coarse or fine. Fine, correct. Problem is solved. Okay, just do one by one, step by step. Soil is fine. Okay, how fine? How are you saying it is fine? We'll discuss it. So first, so you have told that the soil is fine. So how fine? Because more than 50%. Here 62%. Okay, here 62% is actually passing through 75 micron sieve. 0.0075 mm. That is 75 micron. So more than 50% is actually finer than 75 micron. Right? More than 50% is finer than 75 micron. That's why you're calling it as fine soil. Right? So first you have identified it as a fine soil. Now you know it is a fine soil. Now your task is to identify whether it is C, M, or O. So first target is identify whether it is fine or coarse. It is fine. You have identified. Why fine? Because more than 50% is smaller than this one. We're seeing ML. Mm, ML you are saying? No, it's not going to be L. How are you saying this is L? Here liquid limit is how much? 40%. So if yeah, it's 40%, right? So if it is between 35 to 50, what it is? I, right? No, no, no. Why 25%? 25% is the why? How you do it is how so okay. It is 40% is given, right? Liquid limit that is different. That is different portion. It is the liquid limit of oven dried sample. The samples, if you take from the field and if you completely dry it, then also it is going to give you a liquid limit of uh see you take the sample, okay, you do the test, liquid limit test, you will have 40% liquid limit. Now what do you do? You once you again dry the sample once, okay, again you dry the sample in the oven and then again you do the liquid limit test. That time you will see that the liquid limit is coming 25%. So just ignore that part for now. Okay, just see here whatever I have written, just try to take help of this. This is a little different question. Okay, leave it. So see, plasticity index from A line, let us calculate. Same, it is going to be A line and our plasticity index is 40 minus 10, that is 30%. So it is plotting what? Plotting above A line or below. Just a second. Plasticity index is 10%. Sorry, plasticity index is given to you, right? Plasticity index is given 10%. So it is plotting below. So it is going to be M or O. The first part, the first one is going to be M or O. Now tell me whether it is M or O using this hint here. Tell me whether it is M or O. You have identified it correctly. Shubham, you have identified it correctly that it is plotting below the A line, right? Because you wrote ML. That means you have identified it correctly that it is plotting below the A line. So below the A line, it can be either M or O, right? But now using this, you can actually distinctively tell that whether it is M or if it is O. So it is given here, see, if the liquid limit of overnight sample is less than 3/4 of the in situ soil sample, then the soil is organic. So what is the liquid limit of overnight sample? Liquid limit overnight, it's 25%. Now liquid limit of in situ sample is how much? 40%. So 3/4 of 40% is how much? 30. So 25% is less than 30. So this condition is satisfied, right? If the liquid limit of overnight sample is less than 3/4 of in situ sample. This question, this is satisfied. This condition is satisfied, right? 25% is less than 30%. That, so then what happens? The soil is organic. So if it is organic, we will have this O here. Okay. Now you have to identify the suffix. Suffix, tell me the suffix, correct suffix, what will it be? Liquid limit is 40%. It is going to be I. It is going to be OI. So even if you call it MI, even if this question comes and you write MI or OI, it is going to be correct. Okay. It's going to be correct. Yeah. Done. So first we identified that the soil is fine. Right. Then we saw that the plasticity index is lesser than that from the A line. That means it's plotting below. It is plotting below. That means what? That means it is going to be either silt or M or it is going to be organic O. Right. And then the second for the suffix, we saw that. So the liquid limit, it is 40%. That is between 35 to 50%. We called it as high. Okay, right? Very simple. Now let us come to this problem. Classify a soil sample if it has a liquid limit of 35% and plastic limit of 20%. The percentage passing through 75 micron sieve, that is 0.075 mm sieve, is 20%, and the percentage retained on 4.75 mm sieve is 60%. So please try to solve this again. Try to solve, just go step by step. Okay, step by step how to do. Just recall everything and try to solve it step by step. Just try to solve. First, identify whether the soil is fine soil or coarse soil. That you identify first. Coarse soil. Correct. Correct. You have correctly identified the soil as coarse soil. How did you identify the soil as coarse soil? See, less than 50% is actually passing through 0.05 mmc. Correct? Less than 50% is passing through, only 20% is passing through for 0.075 mmc. That means the soil is definitely a coarse soil. Okay, in our case, only 20% is passing through 0.075 mmc. Means definitely our soil is a coarse soil. Okay, coarse. Now, second part is what kind of coarse? Sand or gravel? What kind of coarse? Sand or gravel? It's also very easy to identify. Hmm? Per percentage. Yeah, the percentage retained on 4.75 mm is 60%. That means more than 50% fraction is retained on the 4.75 mm. So correct, you are 200% correct that the soil is gravel. Okay, more than 50% is actually retained on 4.75 mm sieve. That means the soil is definitely gravel. So now out of the prefix and suffix, G is identified. G is identified. Now come to the suffix part. Now what will be the suffix part? What will be the suffix part? Try to tell this. What will be the suffix part? What will be the suffix? Gravel you have correctly identified. Now what will be the suffix? You are saying C. Okay, let us see if it is C or not. Okay, let us see if it is C or not. You said, Shubham, you said that it is C, right? GC. So let us see whether actually it is C or not. Now you're after you've done up to this stage, the next target is to see what is the percentage finer, what is the fine percentage of fine grain. Okay, percentage finer than 75 micron. So here 20% is finer than 75 micron, which is greater than 12%. That means the second part will be either C or M. So this will be either C or M, right? Why am I saying that this is going to be either C or M? Because more than 12% fine fraction is there in our sample. 20% fine fraction is there in our sample. That's why it is the second, the suffix part is going to be either C or M. Now, what is the plasticity index? In our case, 35 minus 20, 15%. And what is the plasticity index from the A line? So obviously 15% is greater than 10.95%. That is, this is plotting above the A line. Correct. This is plotting above the A line. So definitely it is GC. So very good. You have correctly identified. Shubham, you have very correctly identified that it is going to be C. Okay. Very good. Okay. So Vinod, if there is any doubt, you can ask. Okay, anytime. There is no problem. And also try to do this. Try to solve this. So first we identified whether it is coarse or fine coarse, then what kind of coarse, gravel, then so we see the percentage of fine. If it is greater than 12%, it's going to be C or M. Then we decide whether it is C or M. So like this, stepwise we classify it. Now let us come to 9. Problem 9. Problem is classify a soil sample if it has the following properties. Percentage passing 4.75 sieve is 98.5%. Percentage passing 0.075 sieve is 35%. D60, D30, D10 is given, and liquid limit is given, plastic limit is given. Okay, let us try to solve this. Okay, just try once. Step by step again, try to solve. Okay, you are asking in which you have to find Cu or Cc. So if the fine fraction, just listen to me clearly, okay? If fine fraction is greater than 12%, then it will be, we will find plasticity index to get C or M. If the fine fraction is less than 5%, it will be Cu or Cc to decide whether it is well graded or poorly graded. If it is between 5 to 12%, dual symbols, both you have to use. Dual classification we have to use. Okay. So if you see in the previous 20% was the fine fraction, right? 20% was the fine fraction. That's why we determined this plasticity index to call C or M. Now, in the beginning, if you go, for this soil, for this soil, less than 5% is actually less than 5%, 0%, less than 5% is actually lesser than 0.075. That's why we are finding CUCC. Okay. So the more problems you solve, actually, this will be clear. More examples you solve. Just try to solve these examples once again by yourself without seeing the solution. Then it will be crystal clear. Okay, once more you try to solve it. Okay, I hope this is clear. Huh? So try to solve this problem. Classify the soil sample if it has the following properties. Percent passing 4.75 mmC is 98.5%, percent passing 0.075 mmC is 35%, D60 is given, D30 is given, D10 is given. First, first identify whether the soil is what? Coarse soil or fine soil. Go step by step. First, identify whether the soil is a coarse soil or fine soil. Identify that first. You are saying fine soil. Why fine soil? Let us see. Why fine soil? Correct. Now you are correct. It is not fine. It is sand. Coarse soil. Sand and gravel both are coarse soil. It is not fine soil. Why it is a coarse soil? See, less than 50% is passing through 75 micron sieve. That's why we are calling it less than 50% is passing through 75 micron sieve, and more than 50% is passing through 4.75 mm sieve. So if I draw here 4.75. So more than how much? 98.5% is actually passing through 4.75 mm sieve, but only how much? Only 35% is passing through 75 mm. Okay, that means obviously this is a coarse fraction. If more than 55, if here percent passing through 0.057 would have been say 55%, then we would have called it a fine soil. But now it is less than 50%, right? So we will call it a coarse soil. Done. Now what kind of coarse soil? Sand or gravel? Obviously it is sand because almost all of the soil is passing through 4.75 mm. Therefore, it is sand. If more than 50% is retained on 4.75, it will be gravel. So obviously it is sand. Now, what we need to do is that we need to identify a second part. Second part. Now for the second part, okay, for the second part, uh, Second part, what we need to do is that, so you are saying that here 35% is actually greater than 12%, greater than 12%. So let us first calculate CuCC. So what will be Cu? Just a second. Give me a second. Huh? Yeah. So yeah. So we are calling it what? Well graded sand. But why did you calculate CuC? Why to calculate? Why did you calculate Cu and Cc? Just think once. Why did you calculate Cu and Cc? Why did you calculate Cu and Cc? Data is given here. Fine. But why did you calculate Cu and Cc? Correct. You should not calculate, right? There is no point of this data. Why? Because the fine fraction is greater than 12%. It is what? It is 35%. Yes, correct. It is greater than 12%. It is 35%. So obviously, it is you need to focus more on the plasticity index. So let us calculate plasticity index. 22 minus 19, 3%. And from, if you want to see from A line, what is the A line? Now, from this perspective, what will you call it? What will you call it? SC or SM? What will you call it? SC or SM? Tell me. ML? Your soil is sand na coarse. How ML is coming? First, see, there are two parts, that's prefix and suffix. So prefix you have already identified it as S. So just tell me the suffix, whether it is M or C. Whether it is M or C. M. You are telling this is M. You are saying this is SM from this. How are you saying this SM? You are saying this M because this 3% is greater than 1.46. So it obviously it might plot above the LN. So it is M. Like this you are saying, right? Now, if I tell you that no, SM is not the correct classification, what will you tell me then? Now, if I tell you SM is not the correct classification of the cell, so actually this is a critical case. If you see, this is important. This is a critical problem. Now, if you see the chart, see this plasticity chart between 4 and 7%, between 4 and 7%, there is a shaded, there is a two dotted lines that are drawn, right? This portion is a dotted line. Right. If the plasticity index actually falls between 4 and 7%, then what we need to do, we need to actually have dual classification. Okay, in that case, we need to have dual classification. So that can be either, so that is the boundary case. Understood? That is the boundary case. So the final classification can be SCSM like this. This will be the final classification. Understood? This will be the uh, this. Understood? This is a critical case. Between 4 and 7%, if it is there, it will be SCSM. And from here, if you see, from this point of view, if you see directly, it comes out as SC. But there you have to recall one more point, one more factor of this plasticity chart. The plasticity chart says that if the plasticity index is between 4 and 7%, then we need to have dual classification. Okay, if the plasticity index understood, if the plasticity index would have been Understood, na? Okay. This will actually have dual classification. But I have one doubt. Just a second. This one. Okay. I just told you. I just did some mistake. That's why I just got confused. Okay. I was telling you not 4 and 7. See here clearly. This is not about 4 and 7. See the graph properly. Between 4 and 7, there is some dual classification CLML. Okay. You forget about this. Okay. You forget about this. You forget about this. Okay, forget about it. Just see whatever it is written here. Here it is written ML. So between 0 and 4, it is written M, right? M. So our plasticity index is 3%. Obviously, it is less than 4%, right? So that's why you are also writing SM. But if you go through this part, this in from this point of view, you are saying it is a clay, right? It is 3%. So our how much? Our what is our liquid? Liquid is 22% here, 22% somewhere here, and 3% here. Somewhere here it is going to plot, right? That so it is out. See, you just take. Don't confuse. Okay, don't confuse. I'm very sorry. Just don't get confused. Don't get confused. See, IP you calculate first. It comes out as 3%. Then IP from the A line you calculate. It comes out as 1.446%. From this, what you say that it obviously it plots above the A line, so it should be clay. Fine, I agree with you. It should be clay. So one you get C. But one more thing that you have to consider is that this 3% is less than this. Okay, here less than 4%. So our where will our soil plot? Our soil is going to plot somewhere here. Here, okay, here the red dot above 20 I've given here. So here if it plots, but here it is written ML, so it can be silt also, right? So it is just like a very dicey situation. You cannot say clearly. So that's why we write it as SCSM. Okay, obviously the plasticity index is also very low. The higher chances are that it will be SM. Okay, so that is the thing. Okay, so this last problem we will solve. The similar problem was actually given to in the assignment. I'm not sure. So determine the base exchange capacity. So base exchange capacity problem, determine the base exchange capacity of a clay if 100 gram of dry clay soil absorbs 80 gram of calcium. Find the quantity of hydrogen that can be absorbed by 5 cubic meters. Okay. So what is the base exchange capacity? So base exchange capacity is the ability of clay particles to adsorb, not absorb, adsorb. Adsorb means on the surface. Okay, not absorb, not inside, only on the surface. Surface chemistry. To absorb ions on its surface or edge. This is the definition of base exchange capacity. Ability of clay particles to adsorb ions on its surface or now we need to first you need to determine the base exchange capacity of a clay if 100 gram of dry clay soil absorbs 80 milligram of calcium. Now, what is 1 milli equivalent? If you remember for chemistry, 1 milli equivalent is 1 milligram of H plus. Okay, 1 milligram of H plus. Now, what is the atomic weight of Ca2 plus? It is 40 milligram. 40 milligram is the weight of Ca2 plus ions. Now, 1 milli equivalent, you are having 1 mg of H plus, but here two ions are there, right? So 1 milli, sorry. Sorry. Right? Yeah. So 1 milliequivalent is equivalent to 1 milligram of H plus, which is equivalent to 40 by 2. That is 20 milligram of Tier 2 plus, because it has two ions. Right. Therefore, 100. Okay, now it is given that 100 gram of dry clay soil absorbs 80 milligram of calcium. That means 100 gram of dry clay soil absorbs how many milliequivalent? 80 by 20. That is 4 milliequivalent H plus. Okay, so 100. So 100, we are converting it into milliequivalent terms. So 100 gram actually absorbs 4 milliequivalent of H plus. Now our question is the quantity of hydrogen that can be adsorbed by 500 cubic meter of this clay, dry unit weight of clay 1500. So 5 meter cube and weight is given 1500 kg per meter cube. That is how much? 1500 into 5. It is 7500 kg. Right, this much total weight. We need to find out how much hydrogen will be actually adsorbed by 7500 kg of this clay. Now 100 gram adsorbs how much? 40 milligram of hydrogen. So 1 kg, if we convert everything to kg terms, it will be 4 into 10 minus 6 milligram to kg, and this gram to kg again 100 into 10 to the power minus 3. So 75 gram is actually will adsorb to 0.3 kg of hydrogen. So the not you don't have to bother about that much. Just normal. Just once you can see this problem. This is not at all important in geotechnical, the soil mechanics point of view. Just simple. Just once you can just see this. Okay, see this problem. So I just or you can just ignore it for now. But I don't think. But in assignment, I think there was one problem like this. Okay, similar problem. Okay, so that's why I thought that I will solve this problem. Fine. So done. So now what I will do is that I will just share with you. Okay, I will just share with you the uh, this thing. Okay, we'll just share with you the link and all. Just give me a second. Huh?